my friends, now that we have finished discussing the different structures that form in a rock in the primary stages or as a result of applied directed stress or by deformation, the question arises in our minds that how do they form, why do they have this particular orientation or this particular characteristics. For this, it is important to understand about the principles of deformation, the principles of the force applied that causes these deformations. We will also have to discuss about what other factors other than the applied directed stress affect the deformation of a particular rock. The principles and concepts of rock deformation will be discussed over 2 episodes. The first episode will be talking about the physics of the deformation, the applied forces, the strain or change in length and shape of a rock material, the different varieties of the changes that take place in a rock body, and in the second episode we shall be discussing about the factors that control the behavior of rocks under directed stress, the physical factors like high confining pressure, high temperature, the presence of fluids, the effect of time. We shall be discussing these things in the second episode on the concept of rock deformation. The applied force or directed stress that causes the deformation in a rock has been variously described and studied by several workers, both mathematicians, physicists and structural geologists. Here we shall be discussing only the brief outlines, the problems. For greater understanding of the physics of the forces responsible for rock deformation and the effects of rock deformation, textbooks by physicists, written by physicists and engineers, are referred to. Stress or the motive force behind the deformation of a rock is defined as the force per unit area. The stress at a point is defined by the mathematical concept of limit del A tending to 0 F by del A, where del A is an infinitesimally small area around the point and F is the applied force. The force that is acting on a plane, on a surface, can naturally be resolved into 3 mutually perpendicular components. One component acting perpendicular to the plane, one component acting along the plane and in a specific direction in parallel to one coordinate axis of Cartesian coordinates, and the other also acting along the plane but perpendicular to the second one and the other normal to the plane. These 3 components of stress that act on a plane are given different names. The stress or component of stress that acts perpendicular to the plane is called normal stress and is represented by the Greek letter sigma, while the planes acting along the planes are termed shear stresses and sometimes referred by the Greek letter tau, though in modern textbooks the tau has been replaced by sigma again. When the overall stress field in a rock is more or less uniform, the reaction of the material of the rock results in the deformation. But before we go into the deformation part, let us try to understand about the stress field in area. When a rock body is subjected to a directed force, it is always possible to imagine 3 mutually perpendicular planes on which the total stress acting is normal stress and there is no shear stress acting on them. These 3 mutually perpendicular planes are called the principal planes of stress, and if we imagine 3 lines perpendicular to these 3 planes, we can conceive of 3 principal axes of stress. If the length of the principal axes are proportional to their magnitude, then it is possible to imagine an ellipsoid whose 3 major axes are these 3 principal lines. This imaginary ellipsoid with 3 mutually perpendicular but generally non-equal principal axes is called the stress ellipsoid. The stress at a point may be conceived or may be represented by assuming a very small, infinitesimally small cube at that point, the 3 edges of the cube representing 3 Cartesian coordinate axes. On each of the 6 faces of the cube, 3 stress components will be acting, one perpendicular to the face and 2 parallel to the face or along the face and mutually perpendicular to one another. So, total of 9 components, because we have to consider that the force cannot apply a torque to the cube. So, 9 components can completely define the state of stress at a point. If we now go back to the concept of stress ellipsoid, where we have seen that the 3 principal axes are mutually perpendicular and unequal, the greatest principal stress axis is denoted by sigma 1, the intermediate one by sigma 2, and the shortest or least principal stress axis is denoted by sigma 3. It can be mathematically established that if the sigma 1 is a compressive stress, the length being proportional to the magnitude, the shear fractures that develop, they develop at an angle of about 30 degrees with sigma 1 and they intersect along sigma 2. So, technically shear fractures always develop as conjugate sets at an angle of 30 degrees with sigma 1, though mathematically the maximum shear stress should be on a plane that is inclined at 45 degrees to both sigma 1 and sigma 3. Experimental results have shown that the shear fractures or planes of maximum shear stress, they occur at an angle of 30 degrees, making an angle of 60 degrees between the 2 conjugate sets. Now, if we try to go back or refer to the structures that form by fracturing in a rock, by brittle fracturing in a rock, we can see that faults or shear joints, they will develop at an angle between each set of around 60 degrees and about 30 degrees with the greatest principal stress axis when it is compressive in nature. Generally, sigma 3, the least principal stress axis, is tensional in nature, and the extensional fractures that develop in a rock, the tension fractures or tension gashes, they will develop perpendicular to sigma 3. Thus, there will always be an acute angle between the tension fractures and the planes of maximum shear stress or shear fractures, be it a brittle fracture like a fault or be it a ductile shear zone. We have discussed, while discussing the orientation of joints and their relation to the major structures, how pinnet fractures and tension gashes develop together with faults and ductile shear zones, and how the acute angle indicates the direction of displacement along them. From the conception of stress ellipsoid, we can easily correlate the orientation of pinnet fractures and faults and the tension gash veins and ductile shear zone boundaries. Stress is the applied force that causes the formation of structures in a rock, while strain or deformation is the actual measure of the changes in length and shape of a rock body. When a rock body is subjected to a directed stress, it suffers deformation or strain. If we look at deformed rock bodies, we will find that the strain or deformation are of two kinds. One in which originally planar surfaces or straight lines have become curved surfaces or curved lines, and one in which the planar lines and surfaces that were straight before deformation, they remain straight with a fracture separating them. The curvature of planes and lines is known as inhomogeneous strain. It means that there have been differential deformation in different parts of the plane or line, while when a line remains a straight line and a plane remains a plane within the deformed body, the type of strain is known as homogeneous strain. We should keep in mind that straight lines remaining straight and planes remaining planes does not necessarily indicate that their orientations are remaining the same. There may be change in shape without any change in the curvature of the surfaces or lines. For example, a square may be deformed into a rhombohedron or a rectangle. We will be discussing about the various types of strain in the next parts of this episode. The homogeneous and inhomogeneous strain is differentiated on the basis of certain parameters. We will be now discussing those parameters. Strain may be defined in two ways. One, a change in length of lines, and two, a change in the angularity between two sets of lines. When the length of a line is changed, the strain is called longitudinal strain, and when the angle between two original perpendicular lines are changed, it is called shear strain. Longitudinal strain or change in length of lines may be measured or represented by various parameters. If the final length of a line is small l and the initial length of the line was capital L, then the ratio of the final length by initial length or small l over capital L is defined as the stretch. The change in length per unit length, that is small l minus capital L divided by capital L, this parameter is described as elongation and represented by E, while stretch is represented by small s. The next parameter that is used for describing longitudinal strain is called quadratic elongation and is represented by lambda. Lambda is nothing but a square of stretch or small l by capital L whole square. Another parameter generally used for measuring very large strains is natural strain or logarithmic strain. Natural or logarithmic strain is the summation of all small amounts of strain undergone by a line during the entire deformational phase and is represented by a natural logarithm of stretch or L to the base n small l by capital L. The change in angle between two lines or the shear strain refers to the change in shape of a rock body subjected to directed stress. If two straight lines were originally perpendicular to each other and after deformation their angle has become 90 degrees minus psi, that is one line has rotated through psi, then the amount of change in angle or psi is known as angular shear, and for engineers gamma or the tan of psi is known as the shear strain. While in case of shear strain tensor, the shear strain is represented by half tan psi. The total deformation of a rock can thus be described in terms of longitudinal strain, the change in length of the body, and shear strain gamma, the change in shape of the body, a cube becoming a rhombohedral form or a prism. A strained rock body may be represented with the help of a strain ellipsoid. If we consider a sphere of unit dimension present within a rock body before deformation, after deformation this spherical body will take on the shape of an ellipsoid. This ellipsoid, which is the deformed part or deformed representative of an original sphere, is known as the strain ellipsoid. In contrast to the stress ellipsoid, which is an imaginary three-dimensional figure, strain ellipsoids are physically existing figures that can be represented by spherical or spheroidal mineral grains or oolites or fossils or conglomerate pebbles, etc. It should be kept in mind that ductile deformation, in which planar layers are deformed into folds, are examples of inhomogeneous strain, where planes become curved surfaces, straight lines become curved lines, and the values of the different parameters for longitudinal strain, angular shear, and gamma or shear strain changes along any given direction within the body. In our next episode, we shall be discussing how the deformation in rocks is controlled or governed by the physical parameters like temperature, pressure, time, and presence of fluids.